recording, and I would definitely encourage you guys to also turn on your cameras. It's very much helpful for me to see some feedback. Otherwise, it's kind of like I'm talking to myself. And of course, the videos would not be going on record as so yeah. Once again, I would encourage everyone to turn on their videos if that's not an issue. So where were we? We have been in the past few weeks discussing some fundamental concepts of dynamical systems. If I scroll up, so we started with of course the introduction to phase space and how we can see first discrete dynamical systems, and then we moved on to continuous time dynamical systems and what it means. We saw some fundamental results about exploiting the geometry of phase space and what trajectories in phase space mean. And there were some fundamental results about existence, uniqueness, and regularity of solutions, which have played a key role in the examples that we have seen in the past few weeks. So namely, these gave you tools to analyze without really solving the equations, to analyze just the vector field and say whether if I'm starting a solution from an initial condition and I'm observing two solutions, then there's something wrong probably with my vector field with my right hand side. It's not smooth enough. And basically, this already tells you things a lot about a solution, and then what would be required. We namely require Lipschitz continuity to guarantee uniqueness of solutions. And then there was, of course, continuability of solutions and continuous dependence on initial conditions that we saw through various examples. I'm just scrolling through this would be a crash review of what we've been after, just to align myself. And then we were looking, of course, at we saw that there's continuous dependence on initial conditions, which means that if we take a set in the phase space full of initial conditions that vectored under the flow map, which is which is basically which would result in the current configuration of these initial conditions, then this would also be a connected set if we started with a connected set in the first place as an initial condition, right? So this also gave us the chance to locally analyze areas in phase space which are sensitive to initial conditions, and this led to the development of the notion of deformation gradient and the associated Cauchy-Green strain tensors, whose eigenvalues were giving us the FTLE, the finite time Lyapunov exponent, and its ridges were telling us basically the areas which are very sensitive in phase space, and they're prone to separate along these ridges. The solutions or initial conditions are aligned along these ridges, right? So, and finally, in the last week, we were looking at examples of dependence on parameters. So a consequence of smooth dependence on parameters was also that we are able to conclude smooth dependence on initial conditions, right? So this is what we saw, and because of that, because our solutions smoothly depend on parameters, we can Taylor expand our solutions with respect to parameters. And this led to the notion of perturbation, where epsilon was a small parameter with respect to which we could Taylor expand solutions. And then specifically, there was an idea due to Lindstedt, which helped us choose an ansatz where we not only where in this particular example, we assume not just the solution, but also the periodicity of the solution, but also the time period of the solution itself to be depending on that parameter, right? So these were fundamental ideas that were very helpful in sort of analyzing what at a first cut, say, be on a safe ground, what dynamical systems are all about. And moving forward, we would like to understand dynamical systems in a more quantitative sense, or say in a more in some sense, this will be derived from a geometric perspective. In this course, the view is very much that we want to understand the geometric view of dynamical systems, which is also the modern way to see the dynamical systems. And I find it very helpful because once the geometric view is clear, then the algebra sort of, you figure out how to do the algebra. At least if you're like me, I make a lot of algebraic mistakes, but once the geometric understanding is there, then it kind of stays on, right? So, and in continuation with this discussion on geometric analysis of phase space, we are interested in some of the simple features in phase space, which would be, say, fixed points or periodic orbits, and understand how they influence nearby trajectories in the phase space, because that's essentially that's what would give us a qualitative description of what is happening. By themselves, fixed points don't really matter because I mean, this is just a point in the space. You would never be starting an initial condition exactly on the fixed point, right? So the probability of you actually starting an initial condition on the fixed point is 0. So what we are actually interested in, how does the fixed point influence neighboring trajectories? And that's what kind of brings us to this notion of stability. And we have already an intuitive understanding of what stability means. And in the sense that we always go back to the pendulum example, where it has a stable fixed point and it always kind of comes back to its original stable fixed point if there is damping in the system, as you also saw in the exercise classes. But how do we actually define stability? How can we quantify it? And how can we make these notions more precise is what these lectures are going to be about. So please bear with me this week, and let's start the discussion of stability. Before I start, if there are any questions, please, in the material up to now, please feel free to shout out. Okay, if not, then let's start. So this is the second part of the course. So far, we've been, as I was talking about earlier, we've been seeing fundamentals, and now we are interested in stability of simple features, namely fixed points in a dynamical system, right? So, and within this section, the first sort of subsection that I want to focus on is basic definitions. So once again, we have a dynamical system. X dot is f of x t, general non-autonomous system, where x is an n-dimensional phase space. And for the purposes of this discussion, we assume f to be once continuously differentiable, although that is more than what is required for uniqueness. So, but for the purposes of this discussion, I would stick to this. And so this is about fixed points. So assume that our system has a fixed point. Say x naught. And we, without any loss of generality, are going to be assuming that x naught is the origin itself, which means that f of x naught for any time t is 0. Right? So why did I say that this is without loss of generality? Because if not, then if the fixed point is not at 0, then we can simply introduce a change of variables, say x tilde, which is defined as original variable x minus x naught, which is the fixed point, which is non-trivial in case it is non-trivial. And then this would mean that if I want to write the differential equation in terms of x tilde. So if I differentiate x tilde, I get x dot minus the derivative of x naught, which is a constant if it's a fixed point. So that drops out. So I simply get x tilde dot. And the right-hand side would be f of x, which is nothing but x tilde plus x naught. Now x naught is the fixed point, and that's the constant. So we can simply define this this function as we can simply view this this function as a function of x tilde, and we can say call it f tilde of x tilde and times. And now if you see that this new dynamical system that we have in x tilde has a fixed point at origin, right? So if I substitute the x tilde is 0 here, it means that we have this would mean that f tilde of 0 comma t is nothing but f of x tilde f of x naught comma t, which was 0 to begin with, right? Wow, what just happened? Seem to have lost all my notes. I'm sorry for that. Okay, thank God. So yeah, where were we? Yeah, so I was saying that basically, if we see this dynamical system now, if we plug in x tilde is 0 here, we see that x tilde, it means that f of x tilde being 0 is f of x naught comma t, which is nothing by this relationship 0. So which means that x tilde equals to 0 is a fixed point in our new transformed system. So all this just to say that even if you have a non-trivial fixed point, you can assume without a loss of generality after a change of coordinates, then you would be able to come up with a 0 fixed point in the new coordinates. So this is just to simplify our following discussion. And the basic question that we want to analyze is that, given that, granted that this is a fixed point, now what do I do with it? I mean, I know that if I start my trajectory on this fixed point, then I'm going to stay on it forever. But that information by itself is not very helpful. I want to understand how is that fixed point influencing its neighborhood. So the basic question is to analyze the impact of fixed points on nearby trajectories. So for instance, say x naught is a fixed point, a nearby trajectory could simply be spiraling into this fixed point. A nearby trajectory could be just agnostic to it. It doesn't care. It could also be leaving away from it. It could be spiraling out of the fixed point for all I can tell. So the idea would be that the behavior would be observable in case nearby trajectories are coming close to the fixed point. We see that the pendulum, a stable fixed point of the pendulum is stable because when we give it a perturbation, somehow the perturbation decays out and nearby trajectories decay towards the fixed point. That's what actually makes that fixed point observable. Otherwise, there's no point. We could just keep waiting, and we would never be able to observe it. Even if you think that it's imagine the upright position. If we initialize something on the upright position, which is theta equals or theta equals pi, that fixed point is unstable, and there's always microscopic oscillations which would make that fixed point actually unobservable. So stability is something that is very important to assess. So can we actually classify these behaviors via our intuitive understanding of stability? And to that end, we would like to first understand what stability is, and that is the first definition that goes in this section. And it is due to Lyapunov. And I mean, it's of course, I mean, I can always keep waving my hand, but to really understand stability and to say design systems based on our understanding, we actually need a mathematical notion of stability. Otherwise, we can all say, oh yeah, that's stable. It seems like trajectories are going towards that point. That must be a fixed point. It's stable. But no, in order to actually do engineering or any serious applied science, if we need a mathematical definition, and the following definition is basically trying to justify our own or make sense of our own intuitive understanding. And this was something I think very hard back in the day. That's why it's accredited to a person who came up with this notion, and we'll see. So I hope that you guys can appreciate what is to follow. So x naught, x equals 0, which is a fixed point, is called stable. So now stable in the mathematical sense, if for every t naught, so any initial condition that we pick, so somehow we want our solutions in the neighborhood of the fixed point to be confined in a radius around the fixed point. So let's call that epsilon. So let's call that radius epsilon. So given any radius epsilon, we should be able to find some initial condition, so such that all solutions starting from that radius of initial conditions are staying within this epsilon ball. So for every time t naught, initial time t naught, and a confinement radius epsilon in which the solutions should stay, we should be able to find delta, a radius delta, which may be dependent on t naught as well as epsilon in general, such that if we choose any initial condition x naught within that delta radius, we have the solution starting from that initial condition, say x of t at t naught comma x naught, that solution must be bounded within that epsilon ball for all times. So not 0, but t naught. Right, so let's try to, again, this epsilon delta definition is somehow trying to justify our intuitive understanding of dynamic of stability. So let's try to sketch this and geometrically understand it. What are we saying here? So let's say we have the phase space, which is n-dimensional. And on this axis, I assume that we have time, right? So we have time on this axis, t, and here is the initial time, t naught. And on this plane, we have the phase space, say x1 and x2, so on up to xn, right? So what we are saying is that in the phase space, for every initial point t naught, we can choose an initial point, and for every epsilon, so this is a confinement radius in which we want our solutions to lie. So no matter what epsilon, I will be able to tell you what is the radius in which you should release initial conditions such that they would always be contained in this epsilon ball. So let me draw. Oh, this is going to be difficult. Hopefully this works. Oh, great. So this is an epsilon ball. So this is a ball of epsilon radius, which extends through time. We are saying that solutions would forever stay inside this ball for every time greater than equal to t naught, right? So, and we are saying that for every initial condition and every epsilon ball, no matter what epsilon ball is there, there is a delta ball, which is potentially smaller than this epsilon ball. Let me pick another color for that. So this might not seem concentric, but the idea is that it is concentric. Again, this is a ball constructed in the phase space at around the origin, which is the fixed point. So this is the delta ball that we're talking about. So we have an associated tube here as well. And what this definition essentially tells us is that no matter what initial condition I pick within this delta ball, if I start my solution from here, it will sort of go in time. It might end up leaving this delta ball, but forever in time, it would be stuck inside this epsilon ball. So this is kind of the picture that goes in it, which tries to justify our intuition that the solutions would be sort of confined in this epsilon ball forever. And no matter what epsilon you give to me, no matter what epsilon that you give to me, I will find a delta ball which is small enough, close enough to the initial conditions, that if I pick any initial condition in that delta ball, it will always stay inside the epsilon ball. So this could be any initial condition that you pick inside this. It might go outside the red ball, but it will stay always inside the blue ball for all times. So this is basically our solution trajectory, x of t, starting at t naught and x naught. And here is x naught, which is lying inside the delta ball. Are there any doubts about this definition? Then if not, let's try to see this definition in action through an example. And what better to look at than our favorite example, that of pendulum equation. So once again, we have this pendulum, which is say mass m, length l, and the angle we were describing by say x, and there's gravity acting here. And we already saw the phase portrait of this pendulum, assuming there's no damping, it would be a conservative system. And if we were to try and draw the phase portrait, so we know that the orbits around the origin, which is the fixed point, phase space is two-dimensional with position and velocity on the y-axis. So this is the angular displacement, this is the angular velocity. And we know that we already saw in the exercise classes as well as previous lectures that the phase space consists of concentric orbits, which are not really circular, they are ellipses in general. And what we are saying, and we'll see why this exactly why do we need this epsilon delta definition. This is where hopefully you would be able to appreciate the reason for this technical definition, because what the definition tells us from intuition, we know that the origin is a stable fixed point in this system. And so let's say we want, given an epsilon to us, so we want our, what does the definition tell us? That the definition tells us that for any initial condition and any epsilon, which is the confinement radius, we will be able to find a delta. So let me be consistent with the color. So let's say this is the delta that I pick. Okay, so that looks circular enough. So this is the, no, I'm sorry, this is the epsilon. So blue is for epsilon. This is the epsilon ball that I pick. And this is the confinement radius in which I want all our solutions to be confined. And the idea is that this should be symmetric. So please, let me try to quickly erase this. Okay, that looks better. So the idea here is that we know that the orbits are actually concentric circles. They're aligned along the level sets of the energy. And we know that there would be initial conditions we can pick, which would near the origin, which would say lie in this delta ball, in this epsilon ball. But we want to be sure that we cannot pick any initial condition inside this epsilon ball, because for instance, look at this initial condition. If I initialize my trajectory here, even though I started inside the epsilon ball, it turns out that I'm going outside it, right? So the solutions are not really confined to this epsilon ball, but there would be a smaller radius, say delta, that I can pick such that the solutions starting within that delta ball would always be confined to this epsilon ball. So how do I pick that? Simply by looking at this phase portrait, we can geometrically pick it. So in some sense, what we are looking for is another ellipse, which is tangent to the blue ball here. And then we pick an epsilon ball, which starts here at the smaller axis of that ellipse. Just to make it symmetric. Wow, that did not turn out right. Okay, third time is a charm. So now this is my delta ball. Now we can see that Even if I pick any initial condition within this delta ball, I would always be confined to the epsilon ball. See here, if we would be following this, I would be at max going and touching the epsilon ball, but I would always be confined to it. Anything inside this red ball, the delta ball, would be confined to the blue ball. So this is the reason that there's this requirement of this two balls, epsilon as well as delta. And I guarantee you that this is the minimum number of balls that are required here in this example and in the definition. So I hope that example was helpful in understanding Lyapunov's stability, which kind of tells us that the oscillations in this case of the pendulum would be confined if it is conservative, that is sort of aligned with our intuition that around the origin, the oscillations keep continuing and they are controlled oscillations. And the way we formalize that is through this definition of Lyapunov stability. This is very helpful because this does not really, while it's very helpful, it does not really tell us if our solutions are actually decaying towards the fixed point, because that's another thing that would be very desirable in physical systems have damping, and we would not like to have design systems around which we keep oscillating. We would like to have steady states where basically systems are not just oscillating around an operating point, but probably returning to that operating point if they deviate from it. So that brings us to the notion of asymptotic stability, which is the second definition. So a fixed point x equals 0 is asymptotically stable. If, of course, stability is in the name, so it must be stable. So it is stable. And secondly, we want the solutions to decay towards the fixed point. So for every initial condition, no matter what initial condition we choose, potentially in a smaller delta ball, say delta naught, the solutions should be decaying towards the fixed point. So the limit of solution starting at that initial condition for every so sorry, I got to right. So for every, so there should be a delta naught greater than 0 such that for every initial condition inside this delta naught ball, we are landing into the fixed point. So not only do we want stability, but we also want the solutions are sort of decaying towards the fixed point. So the picture that goes with that is, if I can maybe copy this. Okay, perfect. Blow it up a little bit. Is that there should be, so this picture of course applies, we should be stable. So there, for every epsilon, there should be a delta, but also for every epsilon, there should be a delta naught such that, so which would be a potentially smaller radius. No, so it should be a different color, I think. Yeah. So this is a ball of a radius delta naught. And what we are saying is that if the fixed point x naught is asymptotically, if the fixed point origin is asymptotically stable, then no matter what initial condition I choose inside this delta naught, I'm running out of colors. Okay, let's pick this one. No matter what initial condition I choose inside this, and I think I should also erase this trajectory, right? So let me erase these trajectories for now. Okay, so if I choose an initial condition inside this this orange ball of delta naught radius, then what would happen is that as time goes in transient, I might be oscillating, I might even go out, but as time goes to infinity, I would be decaying towards the origin. So this is the behavior that I expect in time, right? So not only would you be confined to that epsilon ball, but as time goes to infinity, you would be decaying towards the origin. You're starting outside that delta naught ball, but still within the delta ball. That's when the behavior that we were discussing might happen. Oh, wow, it converted it into a straight line. Technology can be very helpful, but also sometimes very misleading. So this is what I did not want to say. I'm sorry, once again. Final attempt. I start with an initial condition outside the delta naught ball, but still inside the delta ball, which is the region in between the orange ball and the red ball. So let's say I pick an initial condition here. I started here. This is what leads to the stable behavior. You're still confined to the blue radius, but not necessarily decaying towards the fixed point, right? So this is what is asymptotic stability. Any initial condition starting here would be decaying towards the origin. And naturally, if there is a set of initial conditions which are decaying towards the origin, that means the origin is sort of attracting a neighboring trajectories, and that's what leads to the notion of the domain of attraction. So which is just a fancy name for the set of all initial conditions x naught for which the solution x of t starting from x naught is going towards the fixed point as t tends to infinity. So if there are no questions about the definition, let's look at an application. Once again, of the pendulum. But this time a damped pendulum. So mass m, length L, but this time there is also, say, a torsional damping present. So what this introduces in the equations of motion we assume that this is a linear damping term. So if I were to try and write the equations of motion, this would be the angular acceleration x double dot. Once again, x is the angular angle. X is the angle, x double dot is the angular acceleration. And the moment of inertia of this mass would be m times L square, which provides us the equation of motion. C is the damping constant, which is associated to this damper, which multiplies linearly with the damping. And then there is the restoring force due to gravity, which would be mg. Oh, wow. This is dangerous. Okay, mgl sine x. Right, because that's the force that is acting, and that's the torque that is acting due to gravity. And so let's also assume that that we have slightly perturbed our original system, which was undamped, by adding a little bit of damping here. So damping is a parameter c, which is much less than 1, but it's still positive. And so this means because we have introduced mild damping in our undamped system, the solution trajectories would only slightly perturbed because c is a small parameter that and our solutions, remember, depend smoothly on initial conditions as well as parameters. So if I slightly perturb the system, then initial conditions would from starting from the same initial condition, our solutions over finite time would stay close and would slightly perturb, right? So there's a notion of energy that we can define for this system, which is kinetic energy plus potential energy. So the kinetic energy would be, once again, the moment of inertia, ml squared, times angular velocity squared, plus potential energy, which is mgl times 1 minus cosine x, which comes from the simple consideration that the potential energy here is 0, and then this length ends up being L times 1 minus cosine x. Right. So again, energy is still this much, and the energy, of course, is not conserved. We can still define the energy in this system. Due to damping, it is not conserved. The energy itself is a function of position as well as velocity, kinetic energy plus potential energy. Let's call it E of x and x dot. So energy is not conserved along the trajectories of the dynamical system, which means if we find out the derivative of energy, d dt, dE dt, and along the trajectories x of t, starting from any initial condition, then by chain rule, we would differentiate this expression and we would get the partial of E with respect to x times x dot plus partial of E with respect to x dot times x double dot, right? So, which is nothing but if I differentiate this this expression here with respect to x, I'm only supposed to differentiate this term. This is mgl cosine theta, so I would get the mgl sine theta here. Or sine x actually, or times x dot. And then the derivative with respect to x dot, which is 2 times x dot here, so the half cancels. We have ml squared times x dot times x double dot, right? And in this expression now, I can take x dot common outside, and what I'm left with is mgl sine x plus ml squared x double dot, right? And now if we look at the original equation here, we are evaluating the energy along the trajectories, and it turns out along the trajectories, this equation of motion holds, and if we apply that, we get this term, this term to be simply negative of cx dot, right? So what we get is minus cx dot times, there's another cx x dot here, so this would be cx dot squared. And this is precisely the reason we know that energy is actually decreasing in time, because c is a positive constant and velocity is non-negative. So we know that this would be always non-negative. So energy is sort of decreasing. And now we would like to infer what is the stability of the fixed point in this system. Why were we computing the energy? Because we know that in case of the original pendulum, the level sets of the energy provide us the trajectories of the dynamical system, right? So wow, this is not what I wanted. So once again, I'll try to sketch the phase portrait. It's not bad. Right, so we know that for the damped pendulum, these are, let's say, and for the undamped pendulum, these are the energy levels, but these do not represent the trajectories anymore, right? So a general trajectory which starts at an initial condition here would not be following this level curve, but these are concentric level curves where each the outer one corresponds to a higher level energy. So what we do know is that it would be going, the energy would be decreasing along a trajectory. If I initialize it here, it would start following the trajectory because once again, damping is small, the trajectories are supposed to stay close to the original system. It would be staying close, but the energy would be decreasing. So there's a very close by level set. So this would be kind of going inwards, right? So for as long as x dot is positive, which is the case in the upper half, or it doesn't matter, x dot can be anything. We are squaring it in the end. Our energy will keep on decreasing, right? So energy keeps on decreasing. And you'll realize that the only way we can end up drawing the trajectory then is in this manner. And till the point that when you hit the x equals 0, x dot equals 0, x on the x-axis, momentarily you have 0 rate of change of energy, but then this would mean that you're sort of tangent to another level surface here. But then you would pick on the flow, and once again you would end up in a region where x dot is not 0 anymore, and then you would start decreasing in energy again, and the same logic would follow here until you reach a point where velocity is 0, and then again you would be momentarily, just the energy would not decrease until a point it starts decreasing again. And so you see where I'm going with this idea that the energy is sort of decreasing, and you're starting inside this in this, no matter what initial condition you choose, you would always be sort of decaying. But does this mean that we are actually decaying towards the origin? It's a question to ask, that we know that the energy is constantly decreasing, but does it guarantee, does this mean that it would lead us to the origin? Is this an asymptotically stable fixed point? Because we know that it's stable. We saw that earlier. Is it stable? Yes, it is stable, right? Because I can still, the same logic applies. I can still pick any initial condition, except just like the previous case, we would be able to find for any epsilon a delta red ball such that any initial condition which starts here would spiral inwards. It would only go in actually and stay inside the blue ball always. So, but does it also, we know that it's stable, but is it asymptotically stable? Because for that we would require the energy to be not just decreasing, but going towards 0, right? We want the trajectories to lead to the origin. And what comes to this is actually not, we can always imagine that, yeah, well, a function could always be decreasing, right, and head towards a constant value. It could keep decreasing, and the graph of a function could be, for instance, something like this. And this is something that is not necessarily 0, right? The energy is constant, but are we heading towards the origin? From our physical intuition, of course, we can wave our hands and say that, yeah, we know that trajectories always go towards the origin, but this requires actually a little bit more mathematics than just our hand waving, if we want to actually show that this is a asymptotically stable fixed point. And what comes to our rescue in this case is what is known as the LaSalle's invariance principle. And this is a very general result, not just in this setting, but for any dynamical system. So the setting is the following, which is given a dynamical system, f x dot is f of x. So it's an autonomous system, and we are looking at trajectories which are contained in an open set U of the phase subset of the phase space, right? And once again, there's generalities. I think more general versions of it, but we'll stick to F being C1. So in this setting, once again, we've not talked about fixed points here yet. And we assume that there is a function V, a scalar function, which is also C1, such as the energy that we were talking about in the case of the damped pendulum. And we require that the V dot, the rate of change of V, along the trajectory that should be non-negative, non-positive, just like we had here in case of energy. So far, energy is a candidate function for us, for V. And also we require that if there is a fixed point, if we have any fixed points in this system, in this general system, then that fixed point must be in the set of in the set of points where X, in the set of points X, where V dot of X is 0. So if these three, if these conditions hold, so what is it saying? That we have a function V, which is a scalar function V, which is decaying, which is non-positive along the trajectories of the system. And if we have a fixed point in the system, normally it does not have to happen that V dot of X at evaluated at the fixed point is 0. So the fixed point might not necessarily be in this set, but we require the fixed point to be in this set. So does it happen that, so what is the set of points where V dot is vanishing in our case? In our case, actually, if we treat E to be V, then V dot is vanishing precisely at when X dot is 0, right? So in our case, this set, let's call this set as I, is a set of points where V dot is 0, would be the entire line x-axis. On all these points, the derivative of energy is 0, right? So if this holds, again, I'm still setting up the statement, and then in this case, the set of accumulation points or so to speak, limit points for all trajectories that stay in U. So we are focused in this set U. So we start with all trajectories. We consider a set U in which there's if a trajectory enters, then it stays in it. And this is the kind of set we have here, right? We have a set of trajectories here, say in any of these in ellipses, these would be candidate U's, where we would always be staying inside the U, but we want to find out what is the fate of those trajectories, right? Where do they end up being? So this is what this statement is telling us, that if this holds, then the accumulation points or the limit points of all trajectories that stay in U for all times is in the set of full trajectories in the set I, which is basically, once again, the set over which V dot vanishes in U. Right? So so what does this mean? What are the set of full trajectories? What it tells us is that if there is a set over which we can define a function, there's a tall requirement. Not all systems have this, but in this case, the damped pendulum, we do have such a candidate function, which is the energy, which is continuous, and also it is non-positive. We also know that it has a fixed point, and the fixed point itself is lying on this set. The fixed point is the origin, and it is lying in this set I. In that case, we know that the accumulation points of all trajectories that stay in U for all times, they would eventually be leading to the set of full trajectories in this set I. So what are the set of full trajectories in this set I? We know that any initial condition we start at any point, that would always go away from it. So this set actually does not contain any full trajectory. What is a full trajectory? A trajectory which is contained inside the set I. Can anyone see a full trajectory? Because that would be the accumulation point for all trajectories inside the set U. So far, I have not found any trajectory which is lying inside I. That's what my answer would be. That would kind of tell me where my trajectories are leading. So I'll let you think about it, and I hope to see an answer probably in the chat, if not online. But I want to maybe pictorially describe this idea a little bit. So once again, we have a general set U. In the dynamical system, we know that there are trajectories which lie inside this in this system, or even if they enter, they always stay inside it, right? But they never leave outside the set. Within this set U, we have found a function which is non-negative. Again, this is a principle. I'm not going to be proving this, but this is a powerful result which helps us establish where, if these trajectories, in case this is true, then there would be a set I inside this set. I think we draw it with the red color. And if this set contains, so this would be the set where V dot is 0, is vanishing. And if this set contains any full trajectories, say, of the dynamical system, right? So this should be, for instance, a periodic orbit is a full trajectory. Then we know that all trajectories that are in U, that stay in U forever, would eventually land up limiting towards or accumulating towards this trajectory, which is contained inside I. So one thing to recall is also that fixed points are bona fide trajectories in themselves. So if it's and what we probably should not forget, that there is a fixed point, the origin, which is also a trajectory. we start on it, we stay on it, and it's a full trajectory for all times, right? If we start an initial condition on the origin, we stay on it forever. So basically, then this tells us that in this case, we have a dynamical system where energy is the candidate function, which is non-positive. The origin lies and is the only full trajectory in this case. And what is U here? U can be any set which contains all trajectories, right? So what was the color I used? It was black. So for instance, this could be U. But we cannot keep increasing this U neighborhood because trajectories need to be confined. Remember that if we try to sketch the phase portrait here, it went something like this. We had the separatrices. And outside this, we saw trajectories doing all sorts of behavior. So outside this, trajectories are not really staying inside the set. So any set, so a candidate U would be any set which is contained inside this area, which is defined by the separatrices, right? So this is basically LaSalle's invariance principle is something that I wanted to discuss here, because this is actually a mathematical tool that enables you to conclude that all trajectories, of course, we were able to conclude stability, but asymptotic stability in this case is concluded because all trajectories that stay inside this neighborhood U must eventually land up in the fixed point, the origin, which is the only point contained on the set of vanishing points for V or the energy, right? Are there any questions about this discussion so far? If not, then once again, let's look at another example.
Excuse me?
Yeah, please.
There's a question in the chat.
There's a question in the chat. Okay. If only I can. Oh, there's actually quite a few questions. So, okay, let me take it from the top then. So wouldn't saying for all x naught, there exists a finite epsilon such that any trajectory stays within epsilon also work as a definition without using delta? So I suppose this was a question that was raised before I discussed this example. So that there was a very valid question, and I wanted to address that, but I hope that that it got addressed. So the reason the question is saying that why can't we just use epsilon and say that that's the trajectory itself, precisely because in this case, for instance, we knew that trajectories are not circles but ellipses, and we saw that even though we started inside that ball, we would eventually go out of it. So there needs to be this distinction, right? So the fixed point itself is a trajectory. So this is a question, but actually this is supposed to, I think, answer what I had just asked. And so that's brilliant. I'm sorry that one of the students had actually answered. So that gives me reassurance that you've been following what I've been saying. So, and finally, it says that, yes, it should be an answer. So which is, I guess you guys have been, Okay, no, there's another question that I'm missing, which is, could you also quickly state the exact definition of accumulation points? Okay, yeah, so that's a good question. So let me, before discussing this example, let's say, what is an accumulation point? This is essentially the set of points of a set of points that a trajectory repeatedly keeps visiting over for all sorts of points. So if I try to give an exact definition, so it's a set of accumulation points for a trajectory. Is the set that serve as accumulation points for, say, these would be, if we sample the trajectory at different time instants, then we will see that the sequence of those samples is visiting the accumulation point for arbitrarily long, right? So that sequence has a limit, and so let's call this for the points of for the sequence x of ti, let's call it xi, for some choice, or actually any choice ti, but this should be an infinite set of points such that ti plus 1 is, so this should be an increasing sequence, and ti is going to infinity. Then we would want that, let's say, these points along a trajectory are like this. They don't need to be necessarily equally spaced. Then P would basically be an accumulation point, say, of this trajectory. If this trajectory would be visiting P arbitrarily closely for all times t. So in given any epsilon, so let's say this is an epsilon neighborhood of P. So there would basically be an n such that x n is minus p is less than epsilon. So for any epsilon. So we keep visiting this point no matter how much smaller neighborhood we choose, we would start accumulating towards this point. Yeah, so that would be in some sense a limit point for the sequence of sample points on the trajectory. And so in this case, we know that if this is a limit point, we would always be approaching it. Well, actually, I mean, I didn't want to go into this notion, but the idea is that it's an accumulation point is a point which is approached arbitrarily closely by the trajectory. So in any neighborhood, in any arbitrary neighborhood, you are densely filling up in any arbitrary neighborhood of P, you're densely filling up densely filling up the trajectory somehow, right? So you're keep on approaching the fixed point after a given time, infinite number of times for as long as possible. So that's a point of accumulation. You keep starting here, and you keep getting close, no matter how close, how small a neighborhood that you're picking. I'm sorry, I was not, I think, prepared to give an exact definition, but I think this is a definition that actually works in this case. Are there more questions?
May I ask a question too?
Yeah, so thanks for the answer. So I guess a periodic orbit can also be an accumulation point set, so to speak. Yes, you're right. So you would be approaching points on a periodic orbit. So if it's a limit, or what we call is a limit cycle, actually, it's something that you keep on approaching but never get on it. You keep on approaching it for as long as possible. So that's a good question. Yeah. So that's where you see that this is actually a very powerful and general result. So it does not just apply. We have simplified our example is a very simple application of this LaSalle's invariance principle, which tells us that it's a set of full trajectories that we are talking about, and could be a periodic orbit, and that would be the set of full trajectories towards which you would keep on approaching. So this need not be one set either. If there are multiple fixed points, it turns out that the full set of trajectories would keep on accumulating towards both of them, right? So that's sort of what I had to say about the LaSalle's invariance principle and how we can use it to conclude asymptotic stability of the damped pendulum.
Can I ask one more question?
Yeah, please go ahead.
Yeah, what about the trajectories that fall beyond the separatrix?
Yeah,
do they get affected at all by the damping present?
Yes, that's a good question. So they of course do get affected. I've drawn here in the background trajectories of the undamped system. So this is not necessarily a trajectory of the damped system. They of course do get affected, but the discussion that we are having is based on this scalar function v, which is based on energy, and we know that this energy consideration holds in this set. So any trajectories which come inside this set would be affected, and that's where this result would be applicable. But what can we say about trajectories which are far away? We can't say much. That would require some more concept, and we'll get to talk about that later during this course, or probably in the second half of this course about Hamilton. We'll discuss more about Hamiltonian systems. But this discussion was specifically about energy and have defining a set based on energy, and we know that this is the behavior of that set this is the behavior of energy in the undamped system. And so we can take the set for sure that there is a system and there is a set of trajectories that would always decay, and that is sufficient for us. If we find a set U which is around the origin, then we have found a delta neighborhood, a delta knot neighborhood, so to speak, right? So that's what we were looking for. But that's a good question. So this does not completely tell us this LaSalle's invariance principle, no matter how useful it is, it does not yet tell us what is the ultimate fate of all trajectories in the system, even though we might intuitively be able to say that, oh, they all lead to the stable fixed point. But that's not the case, right? If you think about it, if you give even for a damped system enough energy at the beginning, there would be one particular at least one configuration where you would end up being in the unstable fixed point. So that is not the ultimate fate of all trajectories, but inside a set that is the ultimate fate of all trajectories, and that's how we define that set, right? So I hope that answers your question to some extent. If I look at the chat, I think there are no more unanswered questions, which means we can probably go ahead. Towards the one of the final examples for stability. This was this is example 3. This is an example in polar coordinates. And this is an insightful example because it tells us why do we require in the definition of asymptotic stability first. Why can't we just say, oh, eventually everything leads to the fixed point and that is asymptotic stability, right? Why do we require stability to begin with? And that's a very important distinction, and it'll become sort of clear with this example. So we have r dot is r times 1 minus r, and theta dot, this is polar coordinates, is equal to sine squared theta. If we look at this two-dimensional dynamical system, these are actually two decoupled equations, right? So we can look at them individually and infer their dynamics. In particular, we see that sine squared theta is a positive, is a non-negative number, so it would always be greater than or equal to 0. So in some sense, theta would keep on increasing no matter what initial theta we pick. And the top equation, that of the radius, we see here that it has two fixed points if we look at it as a scalar equation, so which is r equals 0 and also r equals 1, which is where this function vanishes. We can even plot its dynamics, right? So we saw in the lectures that for scalar functions, it's very easy to actually deduce what the phase portrait would be. It's a one-dimensional phase portrait in this case. So r is this. If we plot r dot on the right-hand side here, what we have is a function which is parabolic. So there's 0, there's 1, and this is an upside down parabola, right? So somewhat like this. And we see that the function, the right-hand side is positive in this direction, so r will keep increasing, and it's negative here, so r will keep decreasing here. It's also negative here, so will increase, right? So this is the behavior that I'm sorry, supposed to decrease, right? So this is the behavior that we expect. We have this point, which is all the trajectories are leading to this one, the fixed point one, which means that this is a stable fixed point of the first equation. So when we look at this system individually, we can already say a lot. But if we look at this system as a two-dimensional dynamical system, that too in polar coordinates, then we already know that the r equals 1. That describes actually a complete set, not just one particular point, right? So in fact, that describes a circle of unit radius. And so if we look in polar coordinates, if I'm gonna draw this. Wow, that's a very slanted line. And it's not good at all. You know what? I see that I'm already kind of taking too much of your time, run past time. I'll continue this example tomorrow, and I'll do a better job at drawing this phase portrait. So I will finish this lecture at this point, and we will resume this discussion of this example tomorrow. Very important example, and I think it's very insightful in the sense that why do we actually require stability in the definition of asymptotic stability? Tomorrow, we will also see, actually today, this was an introduction to stability, all these definitions. These are good to know. They give us something to work with, but it does not actually tell us, okay, we know how to define stability and what systems, what fixed points are stable, but how do we actually compute stability? How do we know if a fixed point is stable or not? I'm not going to keep finding epsilon and delta radiuses and keep releasing all possible initial conditions to see what their fate is for infinitely long time, right? Of course, that's not something that is workable in general. So we'll see how we can actually develop some tools which let us assess which let us assess the stability of a fixed point general enough dynamical system. So with that said, thanks a lot for your patience today, and I apologize for minor technical glitches during the lecture, and I look forward to seeing you tomorrow. And if there are any questions, I would be staying on. Well, if not, then it's not an issue, and I'll see you tomorrow.